In the last few lectures, we were examining the pressure driven flow in a pipe, okay, and we had calculated various quantities there. Okay. So, this is the pressure driven flow in a pipe, where there is a pressure difference applied across the ends of a pipe whose radius is capital R. The boundary conditions are that the velocity is 0 at r is equal to capital R, and the stress is 0 at the center, or the velocity gradient is 0 at the axis, because if the velocity gradient were not 0, it would not be uniquely defined. And we had got relations for the velocity as a function of radius. It is a parabolic profile where dp by dx is negative. It can also be written in terms of the maximum velocity, okay, as r square by 4 mu into minus dp by dx. We had got the shear stress, okay, as a function of position, and the shear stress at the wall, okay, and the shear stress at the wall. The average velocity was equal to 1/2 of the maximum velocity. Okay. And finally, I had got the relationship between the friction factor and the Reynolds number, 16 by Re. Okay. And we were solving an example, 2 tanks, tank A with cross sectional area 1 meter square, B with cross sectional area 2 meters square. Tank A is initially filled up to a height of 3 meters, tank B is empty. At time t is equal to 0, you open the valve in the pipe connecting the 2 tanks, and then you want to know how long it will take for the tank to for the fluid to go from one tank to the other through a pipe of diameter 1 centimeter, and the fluid properties, the density of the fluid is 10 power 3 kg per meter cubed, viscosity is 10 power minus 2 kg per meter per second, that is a fluid with a viscosity approximately 10 times that of water. The relationship between the 2 heights emerges from the volume conservation condition. Initial volume in tank A is the area of tank A times the initial height. At any time, the volume is area of tank A times height of tank A plus area of tank B times height of tank B. And from that condition, we got an expression for the height of tank B in terms of the height of tank A, and the difference in heights, okay, in terms of the height of tank A. This difference in height is what is driving the flow between the 2 tanks. Okay. The difference in pressure is because of the hydrostatic heads on the 2 sides. When the hydrostatic heads are different, there is a pressure difference, and therefore, there is a flow going from one side to the other. The pressure difference is also related to the volumetric flow rate. Okay. For a laminar flow, the pressure difference divided by the length of the pipe is related to the volumetric flow rate, which is equal to the area times the change in height of the tank. Okay. Therefore, the volumetric flow rate is equal to the area of tank A times the decrease in height of tank A. So, we had basically equated this V dot, this expression for V dot was substituted into the equation of the pressure gradient and related to the difference in the pressures on both sides divided by the length. Okay. And from that, we got a relation for dHA by dt, okay, which can be expressed as the difference in height from the final steady state height. In the final steady state, the total volume of fluid in the tank is initially 3 meters square, because the area of tank A is 1 meter square and the height was 3 meters. Final height is 1 meter in both tanks. Tank A cross sectional area 1 meter square, tank B 2 meters square, total is 3 meters square times the height 1 meter is the initial volume. So, we had got an expression for the rate of change of the height of tank A with time as the difference between the instantaneous height and the final height when there is no pressure difference divided by a characteristic time. And that characteristic time, we had derived an expression for this, okay, as 16 mu times the area times length by 3 pi rho g r power 4, and I had calculated that for you. okay, 1.36 into 10 power 4 seconds. In this calculation, we have assumed that the flow is laminar. Is it? We calculate that by determining what is the maximum Reynolds number in the flow. The maximum Reynolds number in the flow is related to the maximum volumetric flow rate. The volumetric flow rate, as you know, is equal to minus AA into dHA by dt. Okay, that is the flow rate from tank A to tank B. It decreases the height of tank A and increases the height of tank B. And from this relation here, we know that this is equal to AA into HA minus 1 meters divided by Tc. Okay, that is the volumetric flow rate. The area of tank A times the height of tank A minus 1 meter, okay, divided by the characteristic time which we had just calculated. Obviously, the volumetric flow rate will be a maximum when the height is a maximum, that is at t is equal to 0. Okay. At t is equal to 0, the height is 3 meters. Okay. Therefore, the volumetric flow rate, the maximum value is equal to AA into 3 meters minus 1 meter by Tc. Okay. Area is 1 meter square, okay, of the tank A. So, this is equal to 2 meter square by Tc, 2 meter cubed, okay, because the area is 3 is 1 meter square. So, 2 meter cubed by Tc. Now, the Reynolds number can be written as rho V average d by mu, okay, where d is the diameter of the pipe. Okay. Okay. And I can write the average velocity as the volumetric flow rate by the cross sectional area. Okay. Okay. Which is equal to rho d by mu into 2 meter cubed by Tc into 1 by pi r square. Okay. And you can insert the values here. Okay. You can insert the numerical values for each of these. Rho is 10 power 3 kg per meter cubed. D is 1 centimeter, 0.01 meter, divided by mu is 10 power minus 2 kg per meter per second, into this is 2 meter cubed by 1.36 into 10 power 4 seconds, okay, into 1 by pi into radius square. Diameter is 1 centimeter, radius is 5 millimeters or 0.5 centimeters, 5 into 10 power minus 3 meters, the whole square. Okay. And if you do this entire calculation, you get this as 1875. Okay. Therefore, the Reynolds number is 1875, lower than 2100, even when the velocity is a maximum or the volumetric flow rate is a maximum. Therefore, the laminar flow approximation that we have used for this calculation is valid, okay, even from the initial instance. If it turned out to be greater than 2100, then we would have to go back and try to calculate what the friction factor correlation for that volumetric flow rate is, and then use that in order to find out what is the rate of change of the height. Okay. So, this is an example of the how we can use the friction factor relation, the relation between the pressure difference and the volumetric flow rate for the flow in a pipe, for solving a problem for looking at the discharge between two tanks. Okay. Let us take another problem, okay, friction factor for a power law fluid. Okay. That is, if I had the flow in a pipe of a fluid which did not satisfy Newton's law of viscosity, but rather where the relationship between the stress and the strain rate is given by kappa times dVx by dr into dVx by dr power n minus 1, where n is equal to power law index and this kappa is equal to flow consistency index. Okay, this is the constitutive relation. The momentum balance equation is still minus dP by dx plus 1 by r d by dr of r tau xr. This has to be equal to 0. Okay. That momentum conservation equation is still valid. We got that by the shell balance for the shear stress, but the shear stress is not a linear function of the velocity gradient. Okay. So that is the difference here. And the boundary conditions are, of course, okay, Vx is equal to 0 at r is equal to r, and the symmetry condition dVx by dr is equal to 0 at r is equal to 0. Okay. So those two conditions are still valid in this case. So I can integrate this equation one time to get tau xr is equal to minus dP by dx into minus r by 2. Okay. I had done that earlier for you. Okay. If you recall that in the previous in one of the previous lectures, I had got the expression for the wall shear stress, and here it is. Okay. By integrating the equation in terms of the pressure gradient in terms of the wall shear stress, okay, I had got the wall shear the tau xr as dP by dx times r by 2. We know that dP by dx is negative if Vx is positive. So, that is the reason that I have written this as minus dP by dx into minus r by 2. Now, we have to find out the velocity. This stress already satisfies the condition that dVx by dr is equal to 0 at r is equal to 0. Okay. You can easily verify that if I substitute r is equal to 0 in this expression at the axis r is equal to 0, if I substitute, I will find that tau xr is equal to 0, or the velocity gradient is equal to 0 from this power law relationship. Okay. So now from this I have to find out the expression for the velocity. Okay. I know that k into dVx by dr into dVx by dr for n minus 1 is equal to minus dP by dx into minus r by 2. Okay. That is the equation for the stress, the constitutive relation. Okay. Now, as you can see on the left hand side, okay, this term is always positive. Okay. This term is always positive. Okay. On the right hand side, minus of the pressure gradient is positive, dP by dx is negative. So, minus of the pressure gradient is positive, which means that dVx by dr has to have the same sign as this term here, because minus dP by dx is positive. Okay. So, I can divide throughout by kappa and then take the power of both sides to 1 over n. Okay. So, if I do that, I will get dVx by dr is equal to minus 1 by 2 kappa, okay, into dp by dx, okay, power 1 by n into minus r power 1 by n. Okay. So, I am taking the power on both sides to 1 over n. Okay. In terms of the magnitudes, on the left side have k into dvx by dr power n times the sine of dvx by dr. Okay. So, let me just write that for you. Okay. This is equal to kappa into dvx by dr whole power n into the sine, okay, the sine of dvx by dr. This sine is plus 1 if dvx by dr is positive, minus 1 if dvx by dr is negative. Okay. So, therefore, if minus r by 2 is negative, then the sine of dvx by dr has to be negative. Okay. And therefore, I will get, when I take the power of 1 over n, I will get minus 1 by 2 k dp by dx power 1 by n times minus r power 1 by n. Okay. Integrated once, dvx vx is equal to okay, n by n plus 1 into r power n plus 1 by n, okay, plus some constant c. Okay. A negative sign here, my apologies. This negative sign has to come. Okay. Plus some constant c. Okay. This constant is determined from the condition that at r is equal to r, Vx is equal to 0. Okay. And using this condition, I can easily find out what is the expression for the velocity. Vx is equal to minus 1 by 2 k dp by dx whole power into n by n plus 1. I am sorry. Okay. That is the expression for the velocity. Okay. The maximum velocity is at r is equal to 0. V max that is the maximum velocity at the center of the channel. The average velocity is the ratio of the flow rate and the cross sectional area. Okay. Flow rate we had seen earlier was equal to integral 0 to r 2 pi r dr times Vx. Okay. The differential cross sectional area times the velocity integrated from 0 to r is the total flow rate. That divided by the total cross sectional area by r square of the cross section is the average velocity. Okay. And you can do this calculation. So, this just becomes equal to 2 by r square integral r dr, okay, into minus 1 by 2 k dp by dx whole power 1 by n, n by n plus 1 into r power minus r bar. I can simplify this 2 by r square into and I can carry out this integral. I will get r power n plus 1 by n r square by 2 minus r power n plus 1 by n times r. Okay. So, this term here, okay, if I multiply both of these times r, I will get r power 2n plus 1 divided by n. Okay. R power n plus 1 by n plus 1. Okay. Integral of this. Okay. This is going to be equal to n by 3n plus 1 times r power 3n plus 1 by n. Okay. 2n plus 1 by n plus 1, which is r power 3n plus 1 by n, and I divide by that exponent, okay, when I take the integral. Okay. So, I will get in 0 and r. Okay. So, this will be equal to 2 by r square times, you can see both of these terms have the form r power 3n plus 1 by n, okay, times 1 by 2 minus n by 3n plus 1, okay, is equal to 3n plus 1 minus 2n by 2 into 3n plus 1 is equal to n plus 1 by 2 into 3n plus 1. And you can verify that this n plus 1 cancels out and this 2 also cancels out, okay, and r power 3n plus 1 by n by r square will just be equal to r power n plus 1 by n. Okay. So, is equal to minus 1 by 2k dp by dx whole power 1 by n into n by 3n plus 1 into r power n plus 1 by n. Okay, so that is the final expression for the average velocity. Okay. What is the wall shear stress? Okay. The wall shear stress is equal to kappa into dVx by dr power 1 over n. Okay. Or I can also get it from this expression here for the wall shear stress from here. Okay. Tau w is equal to minus dP by dx into minus r by 2. That is the wall shear stress, okay, at r is equal to capital R. Okay. So, the value of the wall shear stress will be equal to minus, or I will just take the magnitude, minus dP by dx into r by 2. Okay. So, that is the shear stress at the wall. Okay. If you recall, we had also done this by momentum balance along the length of the pipe, and at that time we had got this as d by 4. Okay. So, the friction factor is equal to tau w by rho V average square by 2. Now, I would like to get this in terms of the Reynolds number, okay, because I know that for a laminar flow this has to be proportional to 1 over the Reynolds number. What is the definition of the Reynolds number? We had done it earlier for a power law fluid. Okay. We know that the Reynolds number has to be equal to rho V average power 2 minus n d power n by kappa. Okay. You can see that the wall shear stress tau w, I am sorry, the shear stress tau w is equal to kappa times dVx by dr whole power n into dVx by dr. Okay. If I take the dimensions, the stress has dimensions of m L inverse t power minus 2. Force per unit area, okay, is equal to the dimension of kappa times the dimension of the velocity gradient. Velocity by distance is t power inverse, okay, power n, okay, which means that kappa has dimensions of m L power inverse t power n minus 1. Okay, that is the dimension of kappa. Okay. So, if I have to construct a dimensionless group, okay, consisting of the average velocity and the diameter of this and the flow consistency index kappa, okay, if I have to construct a dimensionless group consisting of these 3 parameters, what I need to do is to, okay, if I take this dimensionless group here, okay, this is m L power minus 3 into L power 2 minus n t power n minus 2 into L power n, okay, d power n is L power n divided by m L inverse t power n minus 1. Okay. And you can see that the mass dimensions will cancel out, the length dimensions will cancel out, and the time dimension will also cancel out, okay, in this case. Okay. And therefore, the flow consistency index, okay, the Reynolds number based upon the flow consistency index has to be this one. Okay. So, we will continue this in the next lecture. Basically, what I have got for you here is the average velocity, okay, and the wall shear stress. Now, I need to find out the friction factor correlation, friction factor in terms of the Reynolds number. So, that completion of the friction factor in terms of the Reynolds number I will complete in the next lecture. I will see you then.